Welcome. Hope you are doing well. In this session, we are going to learn about assembly design in CATIA V5. We will go through a couple of assembly design exercises while learning the commands associated with this workbench. We shall also create drawings of these assemblies. So, first we shall understand the toolbars associated with assembly design. Then, we shall work on making an assembly design of a screw jack and also create a drawing for the assembly. Screw jack is a mechanical device that is used to lift heavy objects by operating a screw. Applications include lifting a car to change a flat tire, lifting foundation of houses, etc. Next, we shall work on caster wheel assembly and then create a drawing for the same. Caster wheel is a wheel that is attached to the bottom of a heavy object to be able to move that object by rolling the wheels of the caster. Example is a shopping cart wheel. Let's take a quick look at the toolbars and the associated commands in the assembly workbench. Some of the toolbars that are accessible in the assembly workbench are product structure tools, constraints, move, assembly features, scenes, etc. Product structure tools toolbar helps with inserting or replacing with new or existing entities like a part or a product into the assembly. Constraints toolbar commands give quick access to all the constraints to arrest movement or to position two part bodies. Move toolbar commands allows us to manipulate the part's position in the graphics area. Assembly features toolbar commands allow us to apply features like split, symmetry, etc. to the assembly. When you want to create exploded views of the assembly, Scene toolbar has the commands to do so. Assembly is a combination of two or more parts to perform a mechanism. In assembly modeling, two or more parts are brought together and placed in their working position. To keep these parts in place, required constraints are applied. Assembly model mainly helps the designer communicate to a manufacturer or a production engineer the process of assembling a product. As part of our first exercise, we shall assemble this screw jack as seen in the picture. I would like to explain to you two different approaches to creating an assembly. One is bottom-up assembly and the other is top-down assembly. Bottom-up is a traditional approach in which part bodies are created individually in part mode. The parts are then inserted, oriented, and positioned in an assembly using constraints. On the other hand, in the top-down assembly design approach, a new assembly file is opened first. Part bodies are created in the assembly itself. The part bodies are modeled relative to other components, and then constraints are applied. However, all the part bodies are saved as their individual files as well. Top-down assembly design approach is usually adopted for conceptualization designs. In the screw jack picture, we can see that there is a base body at the bottom. A nut is sitting on the base body. A screw is fitted into the base body via the nut. A Tommy bar is plugged into the screw from the side. There is a cap above the screw, which is fitted with washer and an M12 screw within. Let's jump into the assembly design of a screw jack using the bottom-up approach in CATIA V5. As part of step 1, we shall start a new assembly window and rename it to screw jack. We shall insert existing parts and position them. In CATIA V5, an assembly workbench can be started by clicking on the File menu bar and then selecting the new option. This action will open a dialog box where we can select the product option to initiate assembly workbench. Another way to do this is to click on the Start menu bar and then under Mechanical Design, select Assembly Design. A new assembly file opens in CATIA. Let's rename this product file as screw jack and save it. Assembly files are saved with a file extension of cat product. If we look at the properties of the product, in the Product tab, the part number field is updated to screw jack. The other fields can also be updated as required. These line items are interlinked with the contents in the Bill of Materials table, which we will see about in the drafting part of this model. I shall click on OK to exit this window. Moving on, in this Windows Explorer, you can see the list of all the parts we need to assemble the screw jack. I need to insert these parts into the screw jack assembly window. I can do this a few ways. If I have these parts open in CATIA, I can right-click on the part name and select Copy. Now I can switch back to the assembly window, right-click on the product screw jack, and then select Paste. This action will include the copied part body to the product specification tree. Now that you are already working in CATIA Assembly Workbench, you may click on the Insert menu bar and select the existing component command. This action pops up the Windows Explorer. You may browse to the location of the parts and multi-select the parts and then click on Open. You can quickly access these commands from the Product Structure Tools toolbar as well. If you are unable to find this toolbar, you may right-click on the rightmost bar on the CATIA window and then check the box beside the Product Structure Tools toolbar. As you can see, in the specification tree, the parts are listed in the order that they were inserted into the assembly. The parts are overlapping each other in the graphics area. At this point, we cannot determine their positions or orientations. Let's separate the part bodies by moving them apart. How do we achieve this? We can use the Move toolbar to manipulate the positions of the part bodies. Let's see how. I will click on the manipulation command from the Move toolbar. Now, if I click on the Drag Along Y-axis button, then select any of the parts, that specific part is activated, and it can be moved along the Y-axis. The selected part cannot be moved in any other direction. The other available options in this window are dragging along a specific plane, axis and rotation along a specific axis. I will click on OK to exit this window. Next, in the Move toolbar, I shall select Snap command. Now, if I click on an axis on the nut part and then select the axis on the screw jack body, these two axes will snap together. This gives the designer a perspective of the positions of the parts while performing the assembly. This does not mean that a constraint is applied between these two parts. The Explode command in the Move toolbar, when activated, will spread all the parts in the graphics area apart. The user will have clear access to all the parts so as to constrain them. In the Explode definition window, the depth field defines the level of the assembly or part in the production structure. This option is applicable when there are sub-assemblies in the product. I will leave the depth field to all levels. I will leave the selection field as is. Update the type field to 3D. For the fixed product field, I will select the screw jack body. Once I hit the Apply button, we can see that all the parts are scattered in the graphics area. Now we have access to all the part bodies to apply constraints. In the next few minutes, we shall learn how to apply constraints to assemble the parts. Then we shall apply color to these part bodies, and then we shall apply a scene operation to create an exploded view of the assembly model. We will be using this exploded view from the scenes in the drawing sheet. As we can see in this picture, the yellow colored part body is the base of the screw jack. I can fix the position of this body using the Fix constraint. To do this, I shall left-click on Fix Component command from the Constraints toolbar, and then left-click on the body in the graphics area or from the specification tree. This action prevents the component from moving from its position during the update operation. Let us now place the nut component on top of the body. In order to constrain two parts in an assembly, 12 degrees of freedom need to be arrested. The 12 degrees of freedom include 6 translational and 6 rotational movements. They are plus and minus sides of X, Y and Z axis, and clockwise and counterclockwise rotations of X, Y and Z axis. Also, Please note that assembly mates or constraints are applied along a point, plane, or an axis, which are considered as reference elements. Back in the assembly, I shall click on the coincidence constraint from the constraints toolbar. I will now hover on the screw jack body to locate its central axis. I will left click on this axis and then, similarly, I will select the axis on the nut as well. In the specification tree, under the constraints branch, we can see the mates that we have applied thus far. Each line item shows the type of the constraint and the names of both the part bodies that this constraint was applied to. Let's see if the nut is moving from its position. To do this, I shall open the manipulation command from the move toolbar like so. If I drag along the X, Y and Z axis, the nut moves in Y and Z directions. It also rotates along the Y axis. But I will not constrain this motion as it is needed for the screw jack mechanism. However, if I click on the update button here, only the linear translation in Z-axis direction stays. The linear translation in Y-axis direction is cancelled out. This is because the motion in Z direction is yet to be constrained for this part. I can do so by applying a contact constraint. I will click on the bottom surface of the nut as shown and then Ctrl left click on the top surface of the base body. Now, I shall select the contact constraint from the constraints toolbar. Upon clicking the update button, we can see that the constraint is applied on these two selected faces. This time, let's use the 3D compass to check the motion of the nut if any. I will left click on the red dot on the 3D compass, drag it onto the nut, and release the mouse button once the plane is aligned as shown. Now, if I click on any of the axes or planes on the 3D compass and move the mouse pointer, then click on the update button, there is no movement. This implies that the nut is fully constrained. I can click on the red dot on the 3D compass, drag, and then release the mouse in the free space in the graphics area to deactivate the 3D compass manipulation. Next, let's constrain the screw with the assembly. I will apply the coincidence constraint between the central axis of the nut and that of the screw as shown earlier. I shall click on the update button to verify the constraint. Next, let us see how the offset constraint works. I shall click on the offset constraint from the constraints toolbar. Then left click on the top surface of the nut. And then left click on the bottom flat surface of the neck of the screw as shown. In the offset value field, I shall type in 60 mm and then click on the OK button. Once I click on the update button, the constraint is applied as shown. Next, I shall apply a coincidence and an offset constraint to align the Tommy bar as shown in the picture. Now, I will click on the coincidence constraint and then I will select the central axis of the Tommy bar and the horizontal axis passing through the hole in the screw by using Ctrl left click and then click on the update button. To apply the offset constraint, select the offset constraint from the constraints toolbar and then I will left click on the vertical axis of the screw and then Ctrl left click on the end face of the Tommy bar as shown. In the constraint properties window, I will update the offset value to -20 mm and then click on the OK button. Observe how the constraint is applied upon clicking on the update button. Tommy bar is now fully constrained except for the rotation along the x-axis, which I will allow for now. Next, I shall mate the cap part body onto the screw. I will use the coincidence constraint between the vertical axis of the screw and the cap as shown. Now, I shall apply a contact constraint between the top edge of the screw and the bottom edge of the cap as shown. Let's click on the update button to update the assembly. The cap is now fully constrained except for rotation along the Z-axis, which I will allow. Moving on, I shall apply coincidence and contact constraints between the cap and the washer part bodies. For the coincidence constraint, I will click on the constraint command first. Then I will multi-select the vertical axis of the cup and the washer. You can see all the constraint symbols in the graphics area. If I hover on any of these constraint symbols, we can see the specification tree highlighting the two part bodies that particular constraint is between. Now I will multi-select the inner face of the cap base and the edge of the washer as shown and apply the contact constraint. I will click on the update icon to update the constraints in the assembly. The last part body left to constrain is the M12 screw. I shall apply the coincidence and contact constraints between the washer and the M12 screw, the same way we did earlier. I will multi-select vertical axis of the cup and the M12 screw and apply the coincidence constraint. Next, I shall multi-select the inclined faces on the washer and the M12 screw as shown and apply the contact constraint. I will click on the update icon to update the view in the graphics area. All the parts are now assembled into the screw jack product. I shall now save the product in a preferred location. Let us apply colors to the part bodies to be able to differentiate them. I will use the color option in the graphics properties toolbar as shown. I am going to hide the constraint symbols in the graphics area by left-clicking on the constraints in the specification tree and then hitting the spacebar on the keyboard. You can do this by right-clicking on the constraints in the specification tree and then selecting the hide or show option as well. I will now click on the Enhance Scene command from the Scenes toolbar as shown. In the Enhance Scene definition window, you may uncheck the automatic naming checkbox to be able to name the scene. I will leave it checked. Next, I will click on OK to proceed further. The software shows a green colored scene mode with a sub-toolbar called Enhance Scenes in the graphics area. I will change the view of the model to front view via the Views toolbar. Next, I will select the Explode command from the Enhance Scenes toolbar. This command does the same operation as the explode we did earlier. I will select Body for Fixed Product field and then click on Apply button. As the message says, we can now move the products using the 3D compass. Let's click on the OK button to exit these windows. I will now drag the red dot on the 3D compass onto the model and place the plane as shown. The 3D compass is placed normal to the XY plane. Now I will click on the nut to make it active and then move the UX plane to align the nut as shown. UX means that the x-axis of the selected body, which is nut here, is not the x-axis of the main product. Next, I will repeat this action on all other parts to place them as shown. Once I finish placing the components, I will drag the red dot outside the model and release it to deactivate the 3D compass. Let's click on the Save Viewpoint command in the same toolbar to save this view. We have the exploded view ready to be added to the drawing. I can click on the Exit Scene command to go back to the Assembly Design workbench. Now in the Assembly workbench mode, under the specification tree, you can see applications under which there is Scenes, and then we have our Scene 1. I can double-click on the Scene 1 to activate it. We can see the view that was created. I will exit the scene. Similarly, you can create multiple scenes as required.